Hi everyone, good morning. So today, I hope most of your questions about the lab will be answered because we didn't cover a lot of the kind of things that you needed to work on the lab questions. So today we're going to be talking about data types in SQL, also how to write conditions in using the where clause, pattern matching, derived columns, and also some functions and operators that will be useful to you in SQL. So let's get started. Okay, I'm going to load my credentials here and connect to the IMDb database. Okay, so in the previous lecture, I said that there is this notion of domain for the column values inside of a table. And I said that the domain specifies what kind of data can go into a column. And today we're going to talk about those kinds of data that are available to us in SQL. And SQL supports Boolean types, character or string types, numbers, date types, and Postgres specifically also supports binary files, which we won't go into the details of that one, but these are the four basic types that we need. Each one of these has subcategories for more specialized purposes, so we're going to be discussing that. Okay, but the main takeaway here is that we call this, the type of the variables that we can use in each column, we call that a domain. That's an important piece of terminology there. Okay, so before getting into that, because we're going to need this type conversion thing in order to discuss column types, let's first see how this works. So when we have a data type of some type and we want to convert that to something else, we can use this cast function. And the way that we use it is very simple. We just put the column name here and we say, okay, cast this particular column or this particular value to that particular data type that we need. The cast function is a standard SQL function. However, we also have a kind of shorthand for that in Postgres, the double column notation, which we can also use to cast variables of one type to another type. This is Postgres specific. The other one is SQL standard, meaning that you can use this casting in MySQL or Oracle DB or Microsoft SQL Server, but this double column notation is specific to Postgres. Okay, let's start with the Boolean data type. Okay, so we can specify this data type using this keyword Boolean or bool, and valid values are for true values, we can use true as string, 1, yes, y, t, and for false values, we can use either the string false, or 0, or no, or n, or f. Okay, let's see how that works. So here I have a SQL cell, and I'm having a piece of string there that says true, and with the double column notation, I am trying to convert that into a Boolean. And I'm doing the same thing with the other strings that I have over there, and let's see if that works. Okay, you can see that the first one evaluated to true expectedly, second one true, third one false, fourth one false. And you might be wondering, what is this particular SQL query that I have written? It is related to the fact that the select statement, we can use the select statement not only to pick particular columns out of our tables, the select statement can also evaluate expressions for us. And this is what I'm using here to print out or convert between these types. For example, I can also do something like this using the select statement. Select 5 divided by 2. Yeah. Okay, and you can see that it evaluates that mathematical expression and gives me the result over there. So we can use select to evaluate expressions as well. And this is what I'm using here. I'm not selecting any value from a table, or I'm not pulling data from any table. I'm just using that select statement to evaluate stuff. Okay, let's get rid of this one. All right. We could have written the same thing using this cast function. So cast, for example, no as Boolean, and that should work the same way, and it does. Okay, but the double colon notation is much cleaner. Okay. So that's about it for Booleans. Let's move on to characters. So there are three main types of string values inside of SQL, and the first type is a character type, or char, and then it accepts an argument n, which specifies the number of characters that it uses. The thing is, with the char type, if we specify, for example, 20 characters, if we have a string that is only 10 characters long, then it will be padded with blank spaces for the spaces that are not used. We're going to have just blank spaces. With the varchar, you specify the maximum number of characters, and then it automatically adjusts itself to that value. And with the text data type, it's the most versatile type. It's a Postgres-specific type, which has no limitation on the number of characters that you can practically store inside of a column value. So technically, I guess it can store anything up to 1 gigabyte of text, but that's a whole lot for just one single value. So practically, you can store any kind of text inside of that. Okay, so let's see how that works. Again, I have some strings over here, and I'm casting those or converting the types. So here I'm converting the type of this one to a character with a maximum number of characters of 50, the other one of varchar with maximum number of characters of 2, and then text. And then when we run that, yes, we can see this over here completely printed. We don't see all of the empty blank spaces. I'm going to show that to you in a second. Inside of Jupyter Notebook, we can't see that. You can see the varchar, the maximum number of characters is 2, so only A and R from my name are retained. And the text type that is both flexible and it doesn't have a limit on the number of characters that it can store. So here, you might be wondering about this character 50. If you use pSQL here, you probably can't use this thing in your terminal because you've installed Postgres in a different way, but you can do that inside of pgadmin. DSCI 513. Okay, so I'm going to just copy the same SQL statement here, paste it here. Okay, and when I do that, you can see that it's padded with blank spaces. Yeah, sometimes it's not blank spaces, it's some special characters for the database management system to know that this is empty, but in Postgres, it's blank spaces. Okay, so again, Jupyter Notebook does not show those blank spaces, as you can see over here. All right. Questions? Yes.
Earlier you did select 5 divided by 2, and then you put a dot after 2.
Right.
Did you have to, because otherwise it would have been 2 division?
Right. Good question. So I kind of skipped over that because I wanted to discuss that later. But when I showed you something like this, so the question is when I divided 5 by 2, why did I put this dot over there? This is because if we don't do that, it kind of just rounds that number and then gives us 2 because it treats both of those values as integers and treats the result also as an integer. If I want this to be like the right way of doing this division, I have to put the dot to specify that, okay, this value is going to be a float. We can also convert this type, for example, to, we'll learn about numeric data types, but to something like that. That also works, but the easier way would be just to put it out there. Okay. All right. So you might be wondering about how to decide what kind of data type to use there. This is actually not our job. This is the job of the person who designs a database, but we still have to know what kind of data, what kind of data types we're dealing with. This is why we're quickly going over these data types. But these are usually decided by the database designers. Okay. Let's move on. The other very important data type are numbers. So we have integers, floating point numbers, and arbitrary precision numbers. Let's see what they are. So integers, just integers, as simple as that. We have small integers, big integers, obviously for different number of digits that we can use in there. Nothing too specific about that, nothing too interesting about that. However, with floating point numbers, we have the real data type that can store almost six decimal digits, and we also have the double precision type, which can store up to 15 or 16 digits after the decimal point, depending on your system. So this second one is equivalent to your float 64 data type, and the other one is equivalent to float 32 inside of Python, for example. Okay, so real double precision. Now, these are inexact data types, meaning that you lose some precision for certain numbers, because when that number doesn't fit in those many bits inside of the memory, the computer just truncates that number and stores the result. That's how computers work. However, we also have arbitrary precision numbers, and this is because databases are, like in a lot of situations, they are used for example, computations that are done in financial institutions, and we want to have as many digits of precision as we like. So for those purposes, SQL also supports these arbitrary precision numbers. So this numeric and decimal, they are the same thing, basically. We have two names for the same data type because of compatibility between the SQL standard and what Postgres implements. So you can just stick to numeric. So with numeric, we can specify the precision that we want, and I'm going to show that to you in a second. But before that, let's just quickly look at integers and then floats, and then we'll get to numeric data type. Okay, so here I have a select statement, and I'm using this cast function to cast that particular number to small integer. And when I do that, you can see that it rounds up the number. Okay, so casting that number into a small integer. All right, another example here is to do the same thing, but using the double column notation. It's the same thing. The result will be the same thing. Okay, now I have this number, which has like many digits after the decimal point, and I'm casting that as real. And real only supports up to 5-6 digits after the decimal point. And if I do that, you can see that we're losing a lot of precision here. So that is equivalent to float 32. Okay. And now, the numeric data type. So with the numeric data type, it accepts two arguments. The first one is the total number of significant digits that we have for that number. And the second number is the number of digits after the decimal point. So let's see how that works. Okay, so this number now got converted to this one, so 183.12. You can see that the total number of significant digits has been reduced to 5, and then we have only retained 2 digits after the decimal point, right? And here, if the numbers are not compatible, then we will get an error. For example, if I do something like that, I'll get an error because it says I can't have 3 digits after the decimal point and also this whole number because I have 183 already. So this is not possible. Okay. But I can use arbitrary precision, 100, yeah, up to the number precision, obviously. Let's say 1, 2, 3, 4, 5, yeah, 9. Oh, yeah. Okay, 9, 3, 12 should be here, and then 9 should be there. Yeah. Okay, so the total number of digits that we have is 12, and we have 9 digits after the decimal point. Yeah. Okay, so 6 plus 2 would be 8, so you have to specify 8 significant digits and 2 after the after the decimal point.
No, I mean, what if we put like 12 digits as 6 and then after decimal 2, like in this case?
Oh, in this case. Okay, so something like that?
No,
6 to, okay. So yeah, this is, yeah, it kind of truncates, rounds the rest of the decimal digits because you're explicitly saying, I want only 2 digits after the, and yeah, where else it can, it cannot invent other numbers before the decimal digits. Okay. So the thing is, you might ask, why are we not using numerics all the time? This is because of kind of the reasons that we've briefly talked about in DSCI 511, and that's because working with data types that have a certain precision is very fast because the programming language, whatever it is, exactly knows what it's dealing with, so it can optimize those computations. It knows that, for example, for each number, it stores, let's say, 52 bits, and then it knows, okay, if it picks every 52 bits, it will retrieve all of those values. So operations become much faster. But with the numeric data type, each time it has to look to see how many digits for the precision we have, and according to that, it's going to do those computations. So it is usually slow to work with. All right. And just to show you that it supports arbitrary precision, you can see that this number was not truncated or anything. It is represented exactly as it is. Okay, questions? Yes? Can you speak up? I can't. Less significant digits. I don't know. I have to check. Yeah, I don't know. Any other questions? Okay, let's move on. So we have talked about the data type in pandas. I'm not going to go into any, too much detail here. I just want to show you that the database management system obviously supports the data type because that's very important. Most of applications that we use day to day, like messaging apps, email apps, like a lot of other things, they use these date times for a lot of their operations, and those date times are going to be stored somewhere in a database, so obviously they have to support this. So just to show you a couple of examples of how these data types work, inside of in SQL, we're going to be covering this a little bit. So we have the data type for dates, time for time of the day, and we also have, so these are kinds of like intervals, but we can also have timestamps, which is a particular instance in time, similar to pandas again. And the timestamp, obviously just a timestamp, but timestamp Z also incorporates the information about the local time zone into that value. And let's see how these work. Okay, so when we have a string like this, we can convert it to a date. Also, Postgres knows all of these other formats and can understand basically what the date is. It also understands words like today or tomorrow. And again, you might be wondering what is the purpose of this string. So sometimes when you're let's say you're changing some values inside of your database and you want to record the time at which something happened. So in your program backend, you just use this word today, and because the column type is date, it automatically converts that keyword today to the appropriate timestamp, for example. Okay, if we run that, we can see that all of these got converted to the right dates, regardless of the format. And you can find a list of the accepted formats in a link that I have provided here if you're interested. Okay, and yeah, this is for dates. Same goes for time. And if I run this, all of these formats are accepted, like that one, 2:24 p.m., and also times with time zone. So this way of denoting time with time zone is SQL standard. And this way is Postgres implementation. So they basically are the same things, but they have different names. Timestamp Z, for example, is the same as time with time zone. Both of them are acceptable in Postgres. Okay, so when we do this, you can see that this time is just stored as a plain time. However, this time with time zone, you can see a -8 hours, and that's Vancouver time compared to Universal Standard Time. Okay, and again, now is stored as this 8:22. However, now time with time zone, it is stored as 8:22 with the offset because of the time zone. Okay, we also have this interval data type, which stores spans of time, basically. And this can be useful for date-time arithmetics, like we've learned in pandas. Not too important here, just for you to see that this is also something possible in SQL. But something that I wanted to show you that I thought was of interest was this, this capability of storing times with time zones. So let's see. Okay, I'm converting this string into a timestamp. And okay, it contains the date, it contains the time. All right. Now, if I do the same thing, but if I use timestamp Z, meaning that I want to store this thing and store the time zone in addition to the time as well, it gives me this. You can see -8 hours, and that's the time zone. Okay. Now, the thing is, the way that Postgres treats this is that Postgres does not store that number over there. Postgres just stores UTC time. So whenever a column is timestamp Z, Postgres just stores standard universal time. And based on the local time zone of the server, it converts that whenever you query the database. So where is this useful? For example, you have a messaging app. The times that you see on your messages, the dates that you see, those are your local times and dates. However, the same message for the other person on the other end will have a different timestamp and different date. This is exactly an application of something like this. So the database has stored universal time, and based on who is making this query, it converts that value to their local time zone. And let's see an example of that here. So here, we have this command, show time zone. It tells us that the server that I'm running on my computer is set to be in this time zone, Vancouver. Okay. And now, I'm going to set the time zone to New York, for example, which has a time difference of 3 hours with Vancouver. Okay. Now, if I take this same time here, where is it? Yeah, this same time step over here, and then store it, yeah, and then evaluate it using my SQL command, but now in the new time zone, you can see that it has automatically converted that to the appropriate value, okay? So it says that the thing that you've given me, this time with time zone, is equivalent to 11:30 with a time difference of an offset of -5 hours. So these two values are equivalent. And you can see that because I have changed my time zone to New York, now the database knows that, okay, this value that I have got belongs to a different time zone, so I have to convert it to the local time zone. So you can see it basically takes care of that automatically for us. We don't have to worry about that. The database designer just sets the column type to be timestamp Z, and then you can store values with the time zones that you like comfortably, and rest assured that the correct values will be retrieved once a user from a different time zone makes a query. Okay, questions? So the takeaway is just that we have a local server time zone, and if we use this particular data type, Postgres or any other database management system stores the time in universal time format and then converts it back to your local time zone once it's needed. Okay, let's go back to Vancouver time zone, print it again, and you can see that we get the same value back. Yeah, it accounts for that, yes. Okay. Yes?
Yes, for example, if you're working right now with the set timestamp, does it store it, and when we open a session again, does it revert it to the original time zone?
Oh, so if you have a column that has the data type of timestamp Z, meaning that I want the time zone to be retained, then Postgres knows that, and because it has saved the universal time, once you query the database, it converts that universal time to your server local time, and that it doesn't matter. Yeah. Okay, just for you to know, not in SQL standard, but in Postgres, it is possible to store images or documents in your tables, just something, an FYI. Nothing important here. It is possible. It's not part of the SQL standard. Okay, let's skip that. The other very important data type is the null data type. So null is just like the NaN values that we had in pandas, meaning that we don't know what the value is. And it has its own data type in SQL. And inside of Jupyter Lab or Jupyter Notebooks, it's going to be shown as none. Inside of pgadmin, you will see null, actually. And in pSQL, you'll see blank spaces for null values. Just be wary of that. Okay, so this is it for data types. Not the most interesting topic, I guess, but something that we had to cover. Questions before moving on to the next part? Okay, something that I kind of just implicitly assumed was that in SQL, whenever we're dealing with string data types, any value that's stored as a string, we always have to refer to that value using single quotes. It's not like Python that you can use both single and double quotes. You have to use single quotes whenever you're dealing with values stored inside of a column, you want to make a comparison or something like that. I will tell you that there is just one situation in which we're allowed to use double quotes, and we have to use double quotes. We will get to that later, but basically know that we have to use single quotes always, almost always. Okay. Okay, we kind of just talked a little bit, not talked, but just I showed you an example in the last lecture about filtering rows with where, but here we're going to go into a little bit more detail about that. So you are familiar with the where clause. There is this where keyword, and then you're going to have a condition, also called a predicate. And inside of that where clause, we can make comparisons using these operators. The most notable thing compared to like typical programming languages is that for equality, we just use a single equal sign, not double equal signs. That's important. And then there's like some other keywords that are useful. For example, for pattern matching, we use like. For ranges, we use between. For selection among a list, we use in. And for null testing, we use is null. And I'm going to go through the details of all of these operators. Okay, so let's take a look at this simple query over here. Select everything, all of the columns from the movies table. That's what we have here. You can see the null values are shown using these nones. Okay. And then, so this query, retrieve rows for movies produced in or after 2010. Okay, so the same query. In the where condition, we have start year greater than or equal to 2010. And yeah, gives us the result that we expect. Nothing too special there. All right, now retrieve the row for the movie called Lost Highway. Do you know who the director is? Yes, that's one of my favorites, that movie. Okay, so we can do something like this, where title equals Lost Highway, and note that we have used those single quotes, okay, because whenever we're referring to data, making comparisons with strings, basically anything about strings, we always use single quotes. So let me run that movie. We can see that, all right. And if I change this, let's just see. Change this to double quotes, it should give an error, yes. It says column Lost Highway does not exist. It says column because of a particular reason that I'm gonna tell you later on. Okay. All right. So now let's move on to logical operators. Okay, we have and, or, and not, and we are at this point we're pretty familiar with how they work, but one important thing about logical operators in SQL is that there is a certain precedence rule, and we have to note that not is evaluated first. Whenever we have a combination of these, not is evaluated first, then and finally or. This is very important. So in the lab, someone came to me and asked me why their where clause didn't work as expected, and there were many different conditions connected to each other with ors and ands, and that was the reason that it wasn't working, because the precedence should be respected. Otherwise, you're gonna see weird results. So here, for example, okay, retrieve rows for movies that are produced in 2015 and are rated higher than 8. Okay, relatively simple case. Start year equals that, and rating greater than 9. Okay, so yeah, meaning that there are no movies with that specification. Something I also just remembered is that if you see some squiggly lines under your SQL code and you don't like those, you can change the cell type to SQL in VS Code, and that will give you the highlighting and also gets rid of those squiggly red lines if you happen to see those. Okay. And now let's consider this example. Retrieve rows for movies that are produced either in 2015 or 2018 and are rated higher than 8. So suppose that we write this condition like that. Start year 2015 or start year 2018 and rating is greater than 8. It makes sense, but when we run that, for example, we see a bunch of movies with ratings below 8. And the reason is because of the precedence that we just discussed. So this and thing is going to be evaluated first, and then the result of this will be passed to this other statement over here. So it's going to say, okay, retrieve the movies that are produced in 2018 and are rated higher than 8, and or retrieve movies from 2015. So this is what it's doing. It's retrieving all the movies produced in 2015. And also, if you look at the bottom of the table, we're going to see movies that are produced in 2018 and rated higher than 8. So this is not what we wanted, but because of the precedence rule, this is what we end up with. So the way to avoid this is by enclosing the conditions that we want to be evaluated first in parentheses. And in this case, I'm saying that, hey, you have to look at this first and then combine the two. So start year 2015 or 2018 and rating greater than 8. If you run that, now all of the ratings are higher than 8 as expected, and we see movies produced in 2015. And we can see that there is a one value of 2018 as well. So this is how it should be written. All right. Okay, questions before we go on break? Okay, let's take 5 minutes of break and we'll be back in 8:42. All right, we're back. So I have a question here for you on the screen, and I want you to work on that for like 2-3 minutes. Okay, so the question is, do you think using the following query, you can find the number of movies in the movie genres table that are not listed as drama? That's the query, and that's the question, and your job is to check whether this query achieves what we have here in the question or not. And you have the IMDb table, and just take a look at, you have the IMDb database, just take a look at this movie genre table, just using like a simple query, and then try to come up with an answer, whether we can do this using this code, this query that we have or not. And this just counts stuff. It's not too important. Okay, let's work on that for a bit. Okay, do we have any potential answers? So let's see what the query is actually saying. So the where clause just says that the genre is not equal to drama, which looks like what we want. And then we're basically just pulling data from the movie genres table, and we're going to count distinct movie IDs. Okay. So what do you think?
Yes.
Okay. So let's have a look at the table and see if we can confirm that. That's the first thing that I would do. I'm going to check out the table just to see what the data looks like. Otherwise, it will be too hard. So here I'm in pSQL. I can use the \c to connect to it because right now I'm in a different database. I can connect to IMDb. Okay. And now I'm going to do select star from movie genres and then hit enter. Okay. So this is the data. Very simple. 2 columns. I have movie ID, and each movie can be categorized as belonging to various genres. For example, this movie ID is listed as comedy, as fantasy, as romance, and so you can see we have multiple rows for each movie. And let's imagine what this query does. Okay, so this movie ID, this one, satisfies this condition, this where condition, because it's not stored as drama. That's probably not a good choice. Yeah, this one is good. Okay, so let's focus on this one. Yeah, this is listed. One of the genres is drama. Okay, so let's see what the where clause does. It basically gets rid of this row, right? But it doesn't get rid of the movie, right? Because even if we remove this row from our results, we will still have that movie ID. And even though we apply this distinct, it just reduces the number to 1. So although we are removing that movie because it's listed as drama, we're not removing all of the rows belonging to that movie. And that's why this query actually doesn't count the number of movies that are not listed as drama. So this is something that we have to be careful about because sometimes it's by default we tend to think that for each entity, for example, here we might take the movies to be entities. For each entity, I'm going to have 1 row. So if I get rid of that row, then I'm good. But sometimes that's not correct. We have to have multiple rows for the same entity to store information about that entity. And actually, this table is not an entity table, it's a relationship table. We're going to look at that more in detail later on. But it was just to prepare you for the kind of things that are coming up later. Okay, so something to watch out for, and something that is useful for when we want to think about retrieving data from databases and getting the right results. Okay, let's move on. So pattern matching. One capability embedded in the where clause thing is to look for particular patterns of strings, and there are various ways that we can look for particular patterns. One is by using the like keyword, which implements the most straightforward, simple way of looking for patterns. This is SQL standard, and it is pretty basic in what it does. If we use a %, it matches any string of characters, and if we use an underscore sign, it matches a single character. So just a wildcard for the % and a single character using underscore. Okay, so for example, here I have this string, for example, in my column, and I say, Arman, is it like this pattern? And UBC, is it like this pattern? So one character before B, another character after B, and also this one. So let's run that. We can see that this is actually like this one because one letter, this string here comes before A, and there is one single character after this A, which is N, so it matches that. For UBC, single character here, matches that one. And for this one, I'm saying MDS is awesome. It matches this part, but it doesn't match that part, which is why it's outputting false. So pretty basic, just % and underscore, that's it. And sometimes that's all we want. Okay, now, just an example here of movies whose title contains the word violin. Okay, and if we do I like, that would be the case-insensitive version of like. Okay. So like and I like is insensitive to the case. All right, and yeah, I have a bunch of examples here. One thing to mention here is that what if we have the percent sign inside of the string itself? So there is this thing called an escape character. We can tell a SQL that whatever comes immediately after a particular character, you can just escape that, meaning that don't interpret that. So here, I'm saying that, okay, any string of characters here and any string of characters here, but because this percent sign comes after this escape character, I don't want you to interpret that. Just take it as is, okay? So here, basically, it means that I'm looking for words or strings that contain a percent sign in the middle. I'm somewhere in the middle. And if I do that, you can see, yeah, so okay, this one here and this one, yeah, these match what I wanted to retrieve. All right. Now, the other useful way for pattern matching would be to use regex. And there are two ways that we can use regex. One is similar to, which is a weird combination between the SQL standard definition of regex and the like syntax, which I don't recommend you using. The other one is that the standard regex, which we can use by using this tilde operator. Okay, so basically we have our pattern, something like this, and then you just use the tilde to show that, hey, this is going to be a regex pattern, and I'm going to use that to match my columns. So here, for example, I want to select movies whose title starts and ends with a digit. And in regex, this caret sign means the beginning of a string. This dollar sign means the end of a string. And here I'm saying that I'm going to have one digit over here and another digit over there, and any number of characters in between. So when I run that, this will retrieve what we wanted. So all of these titles start with a digit and end with a digit. Okay. This is how we can use regex to do pattern matching. And that's about it. Any questions? Yes? You mean the escape thing, this one? Yeah, you can use anything that you like as far as I know. Yeah. Okay. Yes? Oh, yeah. So the question is whether it interprets everything after the escape character or just one character, I guess. So it just ignores the character immediately following that escape character. So here it just ignores this one. And then for the rest, this denotes any string of characters. This also denotes any string of characters. Yeah. Yes?
So if we're trying to look at case sensitivity, what would be better practice, using the I-like or using the I-like or using regex?
Okay, so yeah, so if you're going to use the like syntax, which is simple and it fits your application, then yeah, in that case you have to use I-like in order to make it case sensitive or case insensitive. Yeah, but if you're going to use regex, you have something more complicated, then obviously you have to use the regex way of telling SQL that I'm going to make this case insensitive. Yeah. Okay. All right, so yeah, that was it about pattern matching. And now this very useful operator in, which we're going to use a lot in the topic of subqueries, not something for now. But anyways, so for example, if we have a query like this, retrieve rows from movies, the movies table that correspond to these movies. For example, yeah, this list of movies. So the way that I can write this is that to have a syntax like this, where title equals The first one, Donnie Brasco, title equals The Usual Suspect, title equals Schindler's List, or. But instead of that, we can just simply use this syntax. So title, in, and then a list of values denoted by enclosed in parentheses. So this is what you can see here, title in. So as soon as this title matches any one of these strings over there, it just retrieves the row for us. So basically a shortcut. All right. Okay, we also have another keyword here, again, something that we can use in the where clause for selecting a range of values. It's called between, so we can say, okay, select a column value whenever it's between this number and that number. So here I'm checking this Boolean expression. Is 5 between 1 and 10? Yes. It can also be used for dates. For example, is this date between these two dates? Is this letter between these two letters? And if we run that, yeah, true, true, and false. So just for checking whether a value exists in a range or an interval. Okay, and just note that this is inclusive of both ends of the interval. All right, so we have a query here. I want to retrieve movies that are produced between 2018 and 2020 with a bunch of other conditions which we don't really care about at this point. So the important thing here is just this one. Instead of writing this with a bunch of ors, we just do that using this between. And now, yeah, 2019, 2018, everything between 2018 and 2020. Okay. Now, this one is important. The is null keyword. So whenever you want to find null values, if you do where column equals null, you actually won't get the result that you like or you want. And that's because null means something that is unknown, and two unknowns by definition cannot be equal to each other because we don't know what they are. So we can't say find the null values using that syntax where column equals null. For that, we have this particular syntax called is null, which is designed to achieve this particular purpose here. So, for example, if you want to find movies for which the original title column is null or is different from that listed in the column. Yeah, so when this column contains null values or doesn't contain null values, we can use is not null. And then, yeah, so all of these are filled with values, meaning that there are no unknown values. So basically, just to show you that we cannot use equality with null, we have to use this syntax. Simple, but very important. Okay. All right, so before moving on to the next topic, any question about is null, about between, about, yeah, what about in? Yeah, I guess these are pretty straightforward. Okay. Now, the concept of column aliases. So you might have seen that in the lab, if you happen to have been working on the lab questions, when you do kind of a computation in the select clause, for example, you add a value to a column, multiply that column by a value or something like that, then the column label will become something like question mark, column question mark. It doesn't have a name anymore. In that case, it means that we have a column that doesn't exist in the table, and in order to get rid of that thing, we can give it an alias or a name, basically. And the way that we can do this in SQL is by using this as keyword to give either new names to columns, new labels to columns, or to name columns that don't already exist in our table. For example, here I'm retrieving data from the movies table, and we have this column called title, I want to rename it to movie title. We have this orig title, we want to rename it to original title, and so on. So this works as expected. Now you can see that this has changed, this has also changed, and this one has also changed. Okay. But one important thing to note here is that I mentioned in the last lecture that the select statement is a safe statement, meaning that once you do this, it doesn't actually rename the columns in the table. It's just the way that the data is shown to you. It is just what's retrieved from the database. So you don't need to worry about if those column names are going to be changed. They are just changed momentarily once you retrieve this data. Okay. So now, what is one other thing that's maybe unexpected here? Pardon me?
When you retrieve them, the capital letters.
That's one thing. There's another thing as well. Yes, we have used double quotes, and this is the only place that we can use double quotes in SQL, and that's when we are referring to an identifier. So I told you before in the first lecture that we call the labels of columns or tables or stuff like that, we call them identifiers. And whenever you want to have something as your identifier, as your label, and you cannot use that just simply like this because it will give you a syntax error, you have to enclose it in double quotes. And as soon as you do that, SQL knows that it's dealing with a column name. Okay, double quotes is for column name. And here, the other thing is that this duration has been, the case of the first letter has changed to lowercase, although we had duration is above. And actually, the way to make SQL do this would be to enclose it in double quotes as well. So again, it knows that, hey, I'm labeling this column with a particular value, and I want to be retained as it is. So this is the only place that we can use double quotations. And if you actually use single quotes, it doesn't work, and it will give you error. All right. So the reason that I'm discussing this column alias is first just to give you a way to rename your columns, because sometimes you're going to compute something here and you may want to give it a name in order to make it more clear. And the other reason is that we're going to use this aliases a lot when we work on joins in the next lecture. All right. So now let's discuss this very, very important thing here. I think you're going to have one question about this on the quiz. So let's take a look at this query. Select title as movie title, which title this one, and we have given aliases to all those columns from movie where duration is greater than 100 minutes. Looks pretty harmless, right? I have used the column alias instead of the column name. And when we do this, it says that column duration does not exist. And there is a very important reason behind that. Let me do this. Now this works. So what's different? This is the column alias. In the previous case, it was also the column alias. This here, it works, but okay, let me do this and go back. But this didn't work, so I'm going to put it here just to have a comparison. Okay, so it's basically the same thing. One is a where clause, the other one is an order by clause. The second one works, the first one doesn't work. Yes? And by interpretation, you mean the way?
Start finding the verb first and then try to make the query out of it.
Exactly, exactly. So this relates to the order of execution or order of processing of things inside of a SQL query. And the thing is, SQL is optimized so that if you're filtering some stuff, it doesn't make any sense to work on a bunch of rows that are going to be filtered and thrown away anyways, right? So suppose that you have 1 million rows, and you're going to filter that down to 1,000 rows, and you're going to do something with that 1,000 rows. If you have some computation to be done, it doesn't make sense to do that computation on that entire 1 million rows and then throw most of it away, right? Does that make sense? So this is why when we run a SQL query, one of the first things that it does is that it actually evaluates the where clause. It does the filtering first. And select is one of the last things that it looks at. Okay, so it does the filtering first. And when it does the filtering here, it has no idea about this alias thing. So this is why, in this situation, it gives me an error. In this situation, it doesn't, because order by is something that happens after the select clause. So at that point, it knows that, hey, we have given an alias to this column, and it's fine to use that alias. Now, I have a diagram for you here. This is the order of execution or processing of different elements of a SQL query. So the first thing that the first thing that's going to be processed is SQL looks at which table to pull data from, or join operations, which we'll discuss later. But it looks at from, then it looks at where, then a bunch of other things, then select, and then order by, and all the way at the end, it's going to limit the results. Okay? So you can notice that select is somewhere in the middle, closer to the bottom, and where is way at the top. And you can contrast this to the order of SQL clauses in a statement syntactically. So syntactically, we have select, from, joins, where, a bunch of other things, order by, and limit. This is the way that we write a SQL query. However, the way that it's going to be executed is this way. So there is this contrast between the two. The where condition is going to be evaluated first, then we have select. The way that we have to write it is in this particular order. Okay, questions about that? Yes?
So, like, what would be the way to get around that?
Good question. What would be a way to get around that if we absolutely need to? We will learn about a concept called subqueries, where we can form a query on the side and have the results there and then pull data from that in order to get around it. We will get to that in lecture 4 or 5, I guess. Yeah. Okay. Any other questions about this? So this is pretty important, and I really want you to study it carefully and understand what is the difference between the syntactic order and the processing order of these clauses. Okay. So a lot of errors that you might have with using aliases is going to be related to this very thing that I have just discussed. Okay. So one of the last things we're going to discuss today is derived columns. And this is what we just kind of implicitly discussed. With the select statement, we can not only retrieve data from the columns, but we can also evaluate expressions that involve those columns. So for example, here I'm retrieving title, I'm retrieving runtime, but I'm also dividing that by 60 so that to convert it to hours. And if I run that, it works. And you can see that this is question mark, column, question mark, because this is a new thing. And it doesn't understand, it doesn't have that column in the table, which is why it doesn't know the label for that. And yeah, and here I'm giving it a name, basically, an alias. The same thing. This is an expression, has evaluated to something, and then I'm giving it a title, and now I have runtime hours. So what we have here is called a derived column, meaning that it doesn't exist in the table, but it's something that we have from an expression, the result of running an expression. Okay, This is not very important. Okay, was there any question about derived columns before moving on to the next thing? Yeah. Okay. One other thing that comes in real handy, especially in, I don't know why people designing technical interview questions really like case statements, but just in case you see that, this is how we use them. So whenever you want to print some value or have some value in your retrieve table based on the current values in some columns, you can use the case statement to basically have a kind of like an if-else condition. So we can use it like this. Select this column 1, and then for the next one, when some particular condition is true, then print something else. Okay, and then if none of those conditions are true, then print whatever happens to be in the else statement. So an example is the best way to see how it works. We have title runtime, but for the third column that I want to have in my retrieve table, I'm going to have something like that. I say when runtime is greater than 90, then print long. That's a long movie. When runtime is between 30 and 90, say normal, and then otherwise just stay short. And this is a way of constructing a new column. So you can see that this column didn't exist in the table, and now based on the value that exists in one of the columns, here, runtime, okay, I have a derived column that is constructed using a case statement. Okay. So very useful whenever you want to have a conditional statement and you want to have a derived column based on values in other columns. All right. Any questions about that? Okay. And then, just in 2-3 minutes, I'm going to quickly say that we have mathematical expressions that we can have inside of in our select clause, and you have seen examples of that: division, multiplication, addition. This is just a table showing you a summary of that. If by any chance you had to exponentiate something, you use the caret sign in SQL. Not too important, just to as an FYI. And we also have the kind of the common functions that people might use when using SQL on numerical values. For example, rounding numbers, taking the square root, flooring and ceiling values, absolute values. Those are all available in a pretty straightforward syntax. Again, just want to show you that, not too important. Have an example here of applying those functions on values. And one very important thing here that I think you have encountered in the lab is that some of the functions, like the round function, only works with the numeric data type. So whenever you have the round, you have to cast that particular value of the column to numeric first, and then apply round on that. This is something that happens in the lab. You have to be careful about that. If you get an error there, make sure that whatever is inside this round function is actually a numeric data type, using the double colon or the cast operator. And with strings, again, we have a bunch of functions. For example, to take parts of a string using this substring function, making things uppercase, making things lowercase. Not very important, but it's helpful to have that stuff in mind. This is also something possible to do. One very useful thing here is to use this concatenation operator, the double pipe. If you have two strings, it just concatenates them together. And this is something that you're going to use on the lab. So here, for example, I'm concatenating this title column with these quotes and this with is and hours long and rated something, and then it prints for me a new column that looks like that. Okay, so double pipe used for concatenation. And I guess, a bunch of other functions for date times which are not important for us, kind of optional for this course. And I guess that's it for today's lecture, unless you have any questions. Yes.
What's the difference between char length and length? String.
Char length and length. Actually, I'm not sure. I have to check the documentation. I don't remember. Sorry. Okay. Okay. Thank you, everybody. And I guess I see some of you in the lab today. Thank you.